Hello, hello. Welcome back to the lab. This is EEforEveryone. Today we've got a very exciting video for you. We're kind of closing this next step of the comparator project. We are wrapping up our talk, our discussion, our lecture on Kirchhoff's laws. And we're going to do that by walking through a design example. I'm pretty excited. So without further ado, let's dive in. All right. I was really reflecting on what kind of design example we'd want to do, and I wanted to make sure that we're doing something kind of realistic, something that makes sense. And for me, what that turned into was designing a feedback network for a power supply. This is a pretty common challenge. This is something that comes up quite often, especially in the world of power supplies and electrical engineering. And what that tends to look like is a couple of voltage sources with some resistors. And I really like this example because it's a perfect application of Kirchhoff's laws. It's not an incredibly complex system that would really demand a simulation, but at the same time, Ohm's law would be kind of inconvenient. All right, let's get her drawn. We've got an R1. Got an R2, we've got a V2, and then we've got, and V1 is a control input in this case. And we know it's between 0 and 5 volts. I'm running out of space here, so we're just gonna abbreviate. Okay, so we know this. And we want to design this such that as our control input changes from 0 to 5 volts, the output voltage, V2, should be adjusted between 36 volts and 45 volts. Simple enough. This is our goal. And we know that in order to achieve this, in all cases, this node right here, V, node 2, node 2. There we go. This thing does not like to draw twos. I think it thinks that I'm just like shaking and it turns it into a straight line. Whatever. Let's see if I can draw a reasonably, there we go. Node 2. This must be equal to 1 volt because it's like the feedback node of a controller. I think we've used this example before, but this time we're going to be analyzing it with Kirchhoff's laws. Excellent. So I think that's all we need to know. Here's what I'm going to do. I'm going to first look at this as a node, as a nodal analysis. And yeah, there we go. So we're going to look at this as a nodal analysis first. And in order to do that, that means we need to draw some arrows. So we are going to decide the polarity of our investigation. It's going to be that way. And as we're running through this equation, as we start to build it, we're going to say 0 volts equals voltage at node 2 minus V1 over R1. Followed by voltage at node 2 divided by that 10K known, oh goodness, divided by that 10 kilo ohms. Excellent. Then we're going to get in our third term. There we go. That is the equation. And being completely transparent, I've already done some simplification because I didn't want to make you suffer through that. So if we rearrange this equation for V2, we get V2 equals the node 2 voltage times 1 over R1 plus 1 over 10K times R2 plus the voltage at node 2 node 2 minus V1 times R2 over R1. Perfect. So this is our simplified equation. What do we do with this? Well, we can do a couple things with it. First of all, before we do anything with this, let's look at the bigger picture and make sure that it makes sense. So looking at our system here, right? What do we expect to happen? So the voltage V2 is basically the output of a power supply. Think of it like that. There is some power stage, there is something going on that is using this control signal to drive a power supply and make this output voltage. And so normally what would happen is you just have a normal feedback network, and that would come back through R2 and it'd be a normal resistor divider. But now we've got this extra control signal on that feedback network. So now we've got a second source of current on that lower 10K resistor. Okay. In this case, it happens to be a much lower voltage, but really that doesn't matter. That's kind of irrelevant because we can scale the relative effect of the output voltage and the control voltage based on what we need. Okay, so let's do a quick spot check. What we would expect is that the ratio, the element of V1, the larger V1 would get, and the ratio of that 10 kilo ohm resistor and R1, as well as the ratio of R1 and R2. So it's like the ratio of V1, V2, R1, and R2 are all related. And the correct value for this system depends on everything. But since we're shooting for this 36 volt to 45 volt target, that gives us some bounds. And here's what I've done. We have this SMath worksheet. And this is basically demonstrating the power of that nodal analysis that we've just done. So you can see that equation that we just wrote out. That equation is shown up the top. There we go. Yeah, you can see that. So this right here is that equation that we just described. That's the equation that we just wrote out. I've typed it in for your convenience. And what we're doing is we're defining a function that has those input parameters. Now, over here, we've got three terms, and that's defining the low, nominal, and high control voltage, right? 0, 2.5, and 5 volts. And then we've just gone and spitballed our top, that's basically R2 from our equations before. And you can see that in the R2 field, that last one, that's where we're putting R top, and R div, that's what's coming from the control signal R1 in our calculations, okay? And so now what we can do is we can play with our inputs. This is the voltage that we're regulating to, that 1 volt, that's basically the reference voltage for whatever theoretical controller we might be using. And then of course we plug in our high, nominal, and low control voltages and the resistors. And you can see that, well, this voltage range isn't quite right. We're going from 31 to 57, which is a little bit wilder than what we would really like. So let's think about how we could adjust that. Let's say that we take our div and we make that 120 ohms, or sorry, 120 kilo ohms. Hey, look at that. We've now changed how wildly that swings. How about 140? Look at that. That looks pretty darn close to where we were meant to end up. We're going for 36 to 45, but our range is still a little too big. Okay. So maybe something more like 200 kilo ohms. Great. And you can kind of go through this iterative design. Of course, there are more nuanced ways to do this. There are many other methods. And if you solve the system of equations differently, usually where I would end up is I would solve the system of equations two ways. I would solve it first for either R top or R div, so it's either R1 or R2. And I would use that to plug in the control signal and generate the ideal component value. And then I would start from there and I'd kind of tweak the orderable resistor values until I get something that most closely matches my design requirements. Basically, I would solve the system of equations to find the ideal value of R top given R dith, or the other way around, and then find an orderable set of resistor values for all three that leads to the highest accuracy. Yeah. This is a little bit too guess and checky for my liking, but you get the point. Before we're applying Kirchhoff's current law, that's the sum of all currents must be equal to 0 at a node. Now we're going to apply his voltage law, which is saying that the sum of all voltages in one loop must be equal to 0. It gets a little confusing because when you're applying the voltage law, you're using current, and when you're applying the current law, you're using voltage. Just mental gymnastics galore. Balance in both loops, that means we've got to account for the current from source 2 when we're thinking about source 1. Easy enough. But that poses a problem for this specific design example because I1 and I2 are not fixed. Those are variables. We don't know what those are going to be because we have voltage sources, not current sources. And so the current in either loop is defined by the resistors. So every time we change the resistor, we change the current. So we get into this recursive, we need to go from, since we're designing with voltage in mind, right? We've got V2 and V1. We've got this fundamental problem where since I1 and I2 are both not fixed, it's very difficult for us to finish this system of equations. It's very difficult for us to efficiently finish the calculation because every time we change a resistor, we need to change I1 and I2 since everything's interdependent. Now, if that voltage source V1 were a control current instead of a control voltage, now that would be a different story. That would be easier to account for. Since it's a voltage source, let's just go ahead and finish this off. This is where it gets very messy. Remember what I said in our last videos about how both KVL and KCL have their place, and if it feels like a lot of work to get the calculation done, you're probably doing it the wrong way. This is where I would start to be like, is this really the right way? Because as we go to simplify this equation, let's solve for I2. Look at that beautiful symmetry. Makes sense, right? It's fundamentally the same system. It makes sense that these would be kind of a mirror image of one another. But EEforEveryone, you said this was going to get messy. Where's my mess? Well, here it is. So we need to solve one of those equations for I2. And in this case, and what that's turning into is this beautiful fraction right here, V2. And that is going to be a pain to decompose. What does that make our total equation look like? Oh, I'm glad you asked, because it is not pretty, right? So then we end up, by plugging that back in, so that was with equation 2, by plugging that back into equation 1, we end up with V1 equals, all right, there we go, times 10K. Who wants to solve that? Any volunteers? Huh? No, not me, right? So if we were to do the same thing, if we were to drive this to completion, keeping in mind this picture right here, right? This is the system that we're working with. I1 is not fixed, I2 is not fixed, R1 is not fixed, R2 is not fixed. Like we were saying before, the problem isn't necessarily with the mesh analysis. The problem is that everything's interdependent. So in order to really apply these mesh analysis equations, we would need to fix more resistors. Like if we fix R1, R2, and that 10 kilo ohm resistor, or if we fixed V2, this would be a lot easier. Actually, if we fixed V1 and V2, we could apply this pretty easily. But since both of those are dynamic, oh, that is just such a pain. It would be such a pain to incorporate the this. It would already be a significant effort to break this down into something more conveniently enterable into SMath or whatever computational math tool you prefer. We prefer this one because it's free, much like Noteledge, which is what I'm capturing this in. I love free tools that facilitate learning and teaching and all that good stuff. I love it. I love it. But I hope that you enjoyed this. I hope that you really enjoyed this walkthrough. Yeah, that's just one simple example of how you could use what we just taught you about KVL, KCL, break that down and apply it to something like a switch mode power supply. Just to draw out kind of the application of this in short form. I think we got a little bit of time yet. Oh yeah, we got a little bit of time. So just to draw out, let's pretend it was a brick, right? Let's call this a switch mode power supply. You've got your input voltage, you've got your output voltage, and with some of these modules, they are pretty much like this, except for an external feedback network. And let's say you wanted to add a little trim pot. Something like that. So you'd have a little adjustment, a little dither. Sure, add it in. There you go. There's your hook. Or you could put it basically anywhere in this network, but you could tie it to a voltage source, you could tie it to ground, you could do whatever you want. This would be a similar type of situation where this is the feedback voltage. So that was kind of the application that we used for KVL or KCL. If you want a comparison, check out our video. Check out our video up in the card where we applied that with our simple resistor combination and application of Ohm's law. If you like this video and you can't wait for more, let me know by getting subscribed, hitting that like button, and leaving a comment down below. Coming up soon, we are going to get to the heart of this series by talking about ideal and real comparators. Woo! It's getting spicy. Let's not lose focus. Let's make sure we get to the end. This is going to be a fun wrap up to an excellent series. I can't wait. If you'd like to support the channel, don't forget to hit that like button, get subscribed, and consider checking out our Patreon page linked in the description. It really helps us out a lot, so thank you. Yes, thank you to everyone who has decided to become a member. You're all a big part of keeping this possible. Most of all, I hope that you learned something great today, and I hope to see you again soon. So thanks for watching EE for Everyone, and thank you for staying till the end. Bye.